Pete. We're very grateful to be here today, especially to Diane, Veronica, and the Society for having us. Um, we've had a blast setting up during the exhibit area. Has anyone gotten to check out the exhibit hall and check out the or our booth or the other presenters? I totally recommend the Bio Arcade towards the end. They did a great craftsmanship, and you can play a fantastic video game. So for a good cause. So once again, thank you for joining us today. I'll be brief because I'm right before the last session, so I'm sure you all want cocktails and dinner soon. So um, we'll touch briefly on the things that we're doing. It may seem, I'll preface that it may seem that we're sort of taking a contrarian view on sort of where the technology wave is going. I'll say that given our experience co-architecting one of the most popular deep learning servers in the world at NVIDIA Corporation, and then building APIs at the largest cloud provider. We certainly got to understand what are some workloads and use cases where the cloud may not be the best solution, and that's sort of what we're targeting with our technology. But we'll take a look at some of the computational challenges that we see in bioinformatics and what inspire us to work on the technology that we're working on today and the products that we're building. We also believe it solves a second problem, which is helping researchers cross the chasm of from research to a clinical implementation. We'll show you some of the use cases that we're targeting with some of our early customers, and you're all welcome to go try our system in the exhibit hall. The main computational challenges that we have observed by engaging with some of your peers and some of our early customers is that given the amounts of data that is coming out of experiments, whether it's sequencing, whether it's mass spectrometry, whether it's computational biophysics, the large amounts of data makes it very difficult to write algorithms that are very efficient and computationally optimal. So thereby, there's an increased need for more computational throughput, more memory, et cetera. In use cases like pathology, which I'll give you a brief demonstration. For spatial biology, those data sets can be in the terabytes, and they're very, very difficult to pre-process and get outputs. In a clinical environment, having patient privacy as sort of is paramount, right, to having anything deployed in a clinical environment. So there are some challenges there with encryption and building solutions that meet the privacy and security requirements. And then analyzing and having the precision numerical solutions that are required for, let's say, things like use cases in neurology research, like transcranial magnetic stimulation, where you use electromagnetic fields to stimulate the brain. Those are sort of problems that require very high numerical accuracy and sort of the modern day data structures coupled with the right computer architecture can provide those solutions, but they're not available in a regular computer. Even in most cloud instances, you sort of have very generic computer environments. So we believe sort of, how do you tackle some of these challenges? We believe having, massively parallel heterogeneous compute, meaning being able to couple very powerful CPUs with very powerful GPUs and having a unified memory architecture that keeps memory from moving as little as possible. So having a bigger cache for larger data structures can be very relevant. Is anyone familiar with SIMD instructions? Single instruction, multiple data? Yeah, some of them, some of the folks in the audience. Yeah, so this is a technology that has been around in supercomputing for 3 decades, but the average developer, average programmer, and probably the average bioinformatician is not familiar with it. But these are specific processor instructions that can take vector computation and speed them up significantly. This is what made the GPU. This is actually the technology behind the GPU that makes it massively parallel, and that is also available today in some of the high performance class CPUs and essentially the CPUs that we're using in our systems. So that helps parallelize, algorithms and applications in ways that normally a developer wouldn't be familiar with. And then memory access is another technique in high performance computing. You want to minimize the movement of data, right? You want to have data and be processed in memory banks right where the computational engine is, whether you have a CPU specific algorithm or a GPU algorithm. You want to make sure that transfer of that data is minimized. So, thinking of some of these problems and thinking of some of the technologies that have been available in supercomputing, we went ahead and created an architecture that meets this ideal design requirements, and we build essentially the most powerful computer in the world from the ground up as an inference platform. And not only we build the hardware architecture, but we also optimize every layer of the software stack, from the kernel to the operating system to the drivers to the middleware. And now we are here to partner with you to optimize the application layer, right? Is anyone using PyTorch in the audience? Yeah, good. Yeah, so PyTorch is a framework that we've seen gains anywhere from 30 times to 50 times performance improvement, depending on the network architecture. So that's a framework where we see significant added benefit. So we build this computer. It's a beautiful computer. We kind of compare it to all-in-one beautiful machine. Has anyone gotten a chance to see it in the exhibit hall? Well, good. So all of you are going to come down to the exhibit hall and check it out. So we have two demonstrations in the exhibit hall. We have one where we have a state-of-the-art all-in-one system, and it runs the same digital pathology application. It takes about 30 minutes to perform. We have our system next to it, and it performs the same whole slice scan, same application in under 30 seconds. So it's about 100 times faster. And then we have another application that I'll show you in the front that you're all welcome to try. That is a molecular visualization tool. But we believe this solves the computational problem for the bioinformaticians. A lot of your peers that are very excited about our system are excited for a second reason as well. One is very powerful to solve some of the most difficult scientific compute problems, but two is also an opportunity to take a research pipeline, make it into an application, and deploy it to a doctor's desk side, right? Because this system can be used just as good by a developer as well as a doctor. So very, very unlikely that we could give a doctor a cloud instance and have them process a patient's data, overnight. But if he has the same system where your application was developed, the application can run there. They can rather easily use that application. Big part of the problem that we see today is that in scientific research, in medical research, is that about 98% of the research doesn't go beyond a research paper, doesn't make it through a full pipeline of taking a model that gets trained, building an application, validating that application, and deploying that application in a clinical environment. So we believe this could be a good platform to accomplish that. So we have worked with a number of application developers to accelerate their applications, and that's why we're here today, because we want to partner with anyone developing a pipeline or application to accelerate it and reach a wider user base, wider audience. Some of the demonstrations that we're doing in the exhibit hall, one of it's the digital pathology that I mentioned earlier. We've worked with pathologists to create a benchmark. So we didn't develop the benchmark, we didn't develop the application. We work with them to show the performance can be significant. In some cases, 10 to 20 times faster workflows. The pathology whole slice scans can be very large files that come from a scanner machine, and we've shown significant data there. We've worked with a number of neurology researchers as well to do cortical reconstruction. This is a compute-intensive process. It's used for a number of use cases in neurology. Some of them, like I mentioned earlier, transcranial magnetic stimulation, where you create an electromagnetic field and use it to treat patients. Um, and then the last demonstration, which is available in the exhibit hall, if you go check out the machine, we have a molecular visualization tool called PyMo. Is anyone familiar with PyMo in the audience? Yeah. So if you want to give it a try, go down there in the exhibit hall, play with it, tell us what you think. Um, and just to wrap, I'll show you a quick teaser video that we have been working on. Thank you. Happy to take any questions.
Great talk.
Thank
That
you.
looks really awesome.
Thank you, Patrick.
So one of the major problems too is that, like, SIMD is not the easiest thing to implement either. Is there a way to profile any of your code to see if you're using all like CPUs and there's no like deadlocks happening? Does it show you?
Absolutely. Thank you for bringing that up. So we're making a significant investment in the software tools for profiling. So we're actually doing this extensively with some of our customers now in profiling their pipelines. And for SIMD, we're actually creating frameworks that makes them significantly easier to implement. So I wholeheartedly agree with you. Implementing SIMD instructions has traditionally been very difficult, and our goal is to lower that barrier. So eventually, any developer can learn how to use a SIMD, instruction set. And obviously, a lot of that is processor dependent. So if we're using an x86 processor, they may have their own specific intrinsics. Our systems are mostly ARM-based today. So we have ARM-based specific intrinsics, and then we've developed libraries on top of that, an SDK that you can easily integrate and learn how to use. But like Eigen, are you familiar with Eigen? So with Eigen, when you implement matrix multiplication, you can pick the backend that would be used. So something very, very similar approach.
And is this the same for the CUDA as well?
Same for CUDA to an extent, because CUDA is so mature. There's so much that we can do. There's so much there's only so much we can do to make CUDA. But we work very closely with NVIDIA. I'm actually a former NVIDIA myself, so a lot of the system software from for the GPUs have been very specifically supported and improved for our system. So at the API level, at the application interface level, there's not really much we can do. But
the driver API is a little bit more difficult than the runtime API.
Yeah, and that so those things we've made better. Right. So those things were made better. Yeah, thank you. Thank you. I appreciate that question. Any other questions? Right on. Thank you.
I'll ask a question. This is working. So I'm just wondering, like you're saying you want to optimize the application layer, and so can you briefly describe obviously it's problem dependent, but what's the steps or the process, and what's usually the time frame to do so?
We've optimized everything up to the application, the complete baseline, right? So we have the most performance system you could get available in the market today. And we're starting to publish some of those benchmarks against most available applications or benchmarks like MLPerf or a few others, right? At the application level, obviously the application is the ultimate end user interface, right? So that's where you want to see the best performance interactivity. So there's always some level of work to make that possible. If the application doesn't support ARM, for example, today, we would have to work with the developers to migrate that. We've done that with a number of applications. So we have most relevant applications are supported. If we can build the software from source, is rather straightforward. And then, we're looking for pipelines. We're looking to partner with people we're looking to partner with developers building pipelines that may need additional compute or improved performance. So typically, we're looking for very difficult scientific computational problems that we can help add some value. Thank you. Right on. We're ready for cocktail hour. Thank you, guys.
All right, thank you, everyone.